What, Anthony there?
He
Well, I mean, I think.
debunked gravity with egg and salt.
But what he was taking on the academics. He wasn't just like you know, down here on the ground just arguing back and forth. It was like, right, get your citations out. We've got the references. We've got your experts who say gravity's not a force. You know, so all of that, going with that angle, is what gave him the most hateful response.
Right. And where did it take him? It took him along repeating the bullshit into this year. Then he has a fallout with Ranty, and now he's, you know, where's he going? What's his end goal? Space.
No, I'm just saying the ridicule can get to a person, right? So.
Yeah, but that's not what I'm asking you.
Yeah. So what? What are you asking?
Where's he going with his progress?
Go from a different angle. By a different angle, right? Have to regroup. Go again.
He will be thinking, how can I make some money from this after I've made some money with Roxanne from this by scamming my mate?
I mean, because if he's looking for concessions from you guys, I think like if you have an expectation that you're going to concede that gravity's not a force, and you don't, well then you're obviously like, well, what's the point? Is there any points?
Yeah, gravity's not a force, and I mean the amount of money that they're fighting over is ridiculous. It's less than $500. So
gravity's a force.
No, it's not.
Yeah, it is. It's just a way. It's just a way of looking at it. That's all. It's my definition of force.
My point before you take it on with Babs here. So
sure.
Yeah. Let me just wrap this up real quick. So the idea is that, just like you've just said, Mr. Scott, perfectly, right on time, bang on cue, is that if we're saying to you it's not a force, scientists, we have citations to say it's not a force, but yet you persist to say it is a force. Where do we go from here? So for me, I don't mind, because obviously there's people who need to hear this dogmatic view from you guys, Scott. But for some people, they expect that you should see that it's not a force.
Well, there's citations to say it is a force, and there's an explanation for how to adjudicate it. The thing that you guys seem to be missing is that I'm not just saying it in a flat way. I'm saying that there's a nuance that you guys are missing, which is when you call something a force, it's about a paradigm of looking at it. And so if you're Einstein, if you want to look at it through the lens of Einstein, then it's not a force there. But you don't have to do it that way. There's other ways to look at it. You can model it and think about it in different ways. One of the ways you can think about it is as a force, because a force is something we defined. And by definition, it does meet the requirements.
Yeah, it's like centrifugal force or Coriolis.
Exactly. The effect we witness acts like a force.
Yeah. And I use centrifugal force, whatever you want to call it, a lot when it comes to gravity. You know, when they say, "Oh, it's a pseudo force, so it's not a real force." Okay, well, swing a bucket around. You know, what you're observing is also a pseudo force with the water sticking into the bucket. The real force is centripetal force, but it's still observable.
Sort. Let's bring Sort in. He's wanted to debate or discuss science. Me. Sort, are you here? I mean, this is an opportunity now.
Yeah, I'm around.
Yeah, you're around. Good, man. So, for example, gravity. Is this a force? It's not a force. What is your understanding on this gravitational?
Which is the observation of the gravitational acceleration. It's an acceleration.
So we see things fall. What's the cause? What's the reason? What's the cause to this effect?
The cause is called gravity. That is it.
Okay, so what's actually happening? How we demonstrate?
We demonstrate it by observing the acceleration of things falling.
Yeah, but the acceleration, not the force, is it?
No, it's not force. Force would be the interaction of mass with the acceleration. Acceleration is still a fact. It is the observation. Better?
Yeah, but what we're looking for is the cause to this effect, right? So
No.
something
We're looking at the observation. It's just like a swan. What you're doing is the same with the swans. Because, there is a swan. It is there. We are pretty much sure they're white, all of them. Were at the time we made that term. It's there.
Yeah, again, we know it's there. Yes, we know something's falling. But why? Why did it fall? That's the question. Now you say there's a force, a pulling force.
No, I did not. I said there was an acceleration.
Yeah, but you're saying gravity is pulling this apple or object towards the
Saying
Earth.
gravity is acceleration.
Acceleration is gravity.
This is the observed phenomenon.
I thought gravity was weight.
Oh, that is something it causes.
Gravity
what if you throw a ball and it accelerates? Is that gravity?
Yes, the interaction of mass with acceleration is the force that is gravity. But the gravity itself is not force. Gravity is acceleration.
Okay, so if I throw a ball and it accelerates, is that gravity?
No.
Okay, then shut the fuck up.
No matter the mass,
only gravity
is
accelerates
all the
towards
same.
the ground.
Bro, do you know what acceleration
No.
is? Acceleration. That's why they have the word acceleration. That's why when people say acceleration, they don't mean gravity, because gravity isn't acceleration. If you're a baller, you are perfect
F
baller.
equals MA.
Yeah, now tell me an equation now to turn acceleration into gravity. There you go, that'll work. Use math to prove English. Just like use the sky to prove the ground.
You proved Newton's first law is all you did.
No, you didn't prove anything. You said
threw a
some words.
ball. Did it stay in the air? Did it go forever, or did it come back?
Okay.
Down.
We're talking about gravity and acceleration. I just want to know.
and I'm talking about
is
Newton's first law.
But I'm not. I'm just destroying his thing. All I'm doing is destroying his gravity as acceleration. That's all I'm doing.
Okay.
So we all can agree that gravity is not
acceleration.
acceleration. So
I heard that Richard Feynman said that Newtonian laws of motion were proven to be wrong. I don't know if anybody knows what I'm talking about.
I think it depends on the scale.
It's not relevant.
It sounds like
How is that not relevant when gravity has to do with Newtonian laws of motion?
It sounds like a quote from QE taken out of context.
Let's get a response from Stort, because Stort wanted to discuss this for a very long time. Now he's got a few flat earthers here who are willing to discuss this gravitational force. So I'm trying to let him get through it. So,
sorry, Stort. Away you go.
Yeah. I forgot Babs' question. He asked Stort something.
About Feynman.
Hang on, let me unmute myself. Yeah, I was just saying that someone told me that Richard Feynman, whatever his name is, said that Newtonian laws of motion were proven to be wrong.
Did you look it up? Do you have anything more than someone told me?
Say it again.
Do you have like a source, or like do you have anything we can go on other than someone told you this?
Yeah, hang on. Let me get the link for you.
Now I'll be right back.
Oh, I thought that was me breaking up. Yeah, it was really choppy today.
Yeah. Discord suppressing the.
But one way or another, we're going to sort this out. We're going to find out if you're willing to concede that gravity is not a force, yes? Not a pulling force,
yes.
Not a pushing force, yeah?
I just told you it was observation. It's the acceleration.
Is that a concession then? There is no pulling or push gravity.
Oh, there is there's not a concession of anything. It is just the fact that is.
I just posted the link in the chat for you, Scott. You can take a look at it. It might be cherry picked because I haven't looked at it fully yet, but there it is if you want to see it.
Cool. I've actually read this book before, but I don't remember this part.
Oh, so you do know what I'm talking about?
No, I've read the book before. I'm now on the site, so I know the book. I've read this before, but I don't remember the part you're talking about. So I'll read it right now.
Yeah, I wonder if it's a part that talks about for most things we can use Newtonian when it comes to quantum mechanics. You know what I mean?
That's probably what it means. It means that it breaks down at quantum level. Which we know.
I'm pretty sure that's the one that QE quoted, and then Bob the Science Guy and Blue Marble ripped them apart on it.
Stop derailing here. Thoughts?
I was just talking.
Are you conceding now? Gravity is not force.
Where you got out after that?
Pardon?
Not conceding. It's
not conceding.
It is an acceleration in interaction with mass. That's what I'm saying.
When you say acceleration, do you mean like when a car is accelerated? That's gravity.
You'd have to see it more like a centrifugal force. If you have a carousel just standing there spinning around, and you know if you put things on it, it will be pushed out, right?
Okay.
But it does that all the time. Only you haven't put anything on it. It's still there. Acceleration is still there. That's the point.
Okay. But we're not dealing with mass attracting mass, though, right? Or gravitation. Oh, I have to go.
We're absolutely dealing with the observation that mass. No, we're absolutely dealing with the factual observation. Mass accelerates other mass towards it. That's the premise of making the Cavendish experiment.
Yeah, but they didn't see mass accelerate towards mass. They saw a torsion bar unbalanced. So
that is an attraction. No. That attraction is caused by the observed acceleration.
No, okay, hold on. What you actually have, right? The empirical thing you have is a torsion bar unbalance. Now you're going to say, well, that can only happen because, and then you just left reality and moved into beliefs and religion.
Nope.
So if it moves, would you agree? If I took a magnet, that thing, and it moved towards the magnet, that would be the magnet pulling it, right?
Okay, magnetism is not gravity. First off,
would you agree?
Well, I know. We're just talking. But do you agree that magnetism is not gravity?
Yes, absolutely.
Okay, and do you agree that when you put a magnet towards the object, you see the object go towards the magnet, not a torsion bar twisting, right? We agree on.
There's no, you're not getting the torsion bar bit right.
No. But here, this is what you're not getting. With the magnet, you can see the object move towards the magnet. With your Cavendish, you never see that. You get torsion bar twist, and then you have to assume that there's some very small force.
Oh.
No, you don't see mass. If you could see mass attracting mass, you wouldn't need the torsion. Hold on. If you could see mass attracting mass, you wouldn't need the torsion bar to convert that small little force into something that can be quantified through the torsion bar. So don't give me your bullshit.
Don't show you a video happening.
Don't give me your bullshit.
That's exactly why you need it.
If you're telling me you can see a force that pulls with 1/500 billionth of a, then okay, yeah, then you're fucking stupid. Then I should be able to see my car pulling a golf ball. I should be able to see my house pulling a piece of dust that falls next to it. You don't see any of this stuff, so you're just wrong. The only thing. The only thing. I know. I know. I'm childish. Okay. So the only thing. And now the interruption comes and the over talking.
Well, to be fair, you're sort of running into rant mode. Yeah, just everybody calm down.
I already know what the response for this is going to be. You're just going to say that the attraction is proportional to the size of the body that is being observed. So
it is.
And
so the Earth is the biggest.
Well, what do you want us to say? That's the truth.
A skyscraper's pretty huge. A skyscraper's huge. Why doesn't it pull a baseball towards it?
Because the Earth.
Okay, but but then why is it
Cavendish?
So you're going to say that you can have
because Cavendish set up a condition.
Oh, he had the torsion bar. Yeah, he had the torsion bar.
Hey, right. You're interrupting like crazy. Can you just relax on the slide? We'll say stuff too. So, yeah, he set it up so they would be very, very isolated. But in normal life, like just walking around that skyscraper, too many other forces are acting on you for that skyscraper to have any effect.
Okay.
And it's big, but it's not anywhere near big enough.
Okay, let me ask you. Can you see mass attract mass, or can you only set up an experiment with a torsion bar that will
No, you can see it.
Okay, where can I see? Okay.
I uploaded
So what you want to look into, there's at least 2 famous experiments that you would probably want to check out. There's one called like I'm blanking on the name. So the Sherendruk Mountain or something. It was around 1870. Schehallien Mountain. Yeah, Schehallien Mountain. Thank you. Schehallien Mountain. And so you want to check that one out because that's where they found a really symmetrical mountain. Went and held up basically a plumb bob and found that the plumb bob was pulled towards the mountain. And then there's also a video.
Wait, before, okay. So before we go in there, because you're saying that mass attracts mass. Now, didn't we already go over that mass is a quantified measure of the amount of matter? And weren't you the one that said there's 9 or 10 definitions that says mass is the measurement of matter? Weren't you the one that was saying that?
Yeah,
okay, so now okay, so stop. Okay, so now you're going to tell me that you, who have read the definition of mass and asserted that it is a measurement of matter, you're now going to tell me that that measurement can pull other measurements. This is why.
Yeah. So first of all, you
can't say nothing now. You're done. You.
Of course, I can say something now because you've just said stuff for me that you said was incorrect. You said incorrectly. You're like literally making up a story about what I said, making up an interpretation of what I said, cutting me off if I answer in any way, and then telling me that I'm done. It's ridiculous.
Scott, why called you a retard?
Mr. Scott, so here's the deal. Is the word mass refers to is a measurement and it refers to the matter. The same way that temperature is a measurement and refers to heat. Okay, so mass can refer to both, and I don't think mass attracts mass in a causal way. I think it attracts. It appears to be moving towards each other as if it's causal, i.e., it's correlated. Is what I think.
Do you concede that?
I don't know. I don't know if it's causal.
Do you concede?
But it is correlated.
No. Do you concede it's not a force?
No, I don't. Of course not. It is a force.
You just said it looks.
Wait, hold on a sec. Mass does attract mass because protons can be shown to attract neutrons, but not the way you guys are describing it. You guys are describing
it's a correlation. What we're describing as a correlation. There's two variables that go into the equation. One is distance and one is mass, and there distance is inverse and it's to an exponent, and mass is linear and proportional.
Okay, and Scott, you've been talking a lot. Is mass the measurement?
Oh, nowhere near as much as you, though.
Okay, hold on, let me get this out. Is mass the measurement of matter, or is mass the measurement of matter and the matter? Which one is it?
It's both.
Okay, so when you say mass, you're not just talking about the measurement of matter. You're talking about the actual matter.
Yeah, you can be referring to the actual matter.
Okay, so if I said I have a mass of rocks, you would know how many rocks I'm talking about because I gave you the quantity. Oh, okay. So mass isn't the actual. So when
if you didn't give me a quantity, I wouldn't know. I just have to. If you didn't give me the quantity, you could say I have a distance, and I know you have some number of feet, but I wouldn't know how many feet.
Okay, hold on. So is the mass of the rocks, or are the rocks the rocks? And mass describes how many rocks.
What?
Okay, let me make my point. Let me make my point clear. So the other day you said, and Scott was arguing against ballers who were saying mass was more than a measurement. And we can go read. I have the thing saved. We can go read all of the definitions. Mass is the quantitative measurement of matter. It never says mass is the matter. So what you're doing,
that's what it does sometimes.
Hold on, I know, but just listen. And what you're doing is what you're doing is semantical word games to try and make matter, right? You're saying you can't use matter attracts matter because that sounds so stupid. Because if you had matter sitting next to matter, you would know it's not attract. So you can't use that. So you got to say mass, right? You say, well, mass attracts mass. And then we find out what mass is, and you go, well, it's matter. It's matter basically. It's just a collection of matter. So
I don't say either one of those things.
Hold on, but I'm not done. So just sit and listen. So the idea that you're turning matter right into mass and a measurement, like that's where you're going wrong. So mass.
But I don't say the first thing in the first place. I don't say that matter attracts matter or mass attracts mass. I don't give a causality to it, right? I say it's correlated. So you can look at two masses. You can determine how much the strength of the attraction force is going to be by determining what the two masses are and how far away they are. And just quantified it then. And when you say I'm playing semantic games, I'm telling you that if you look at these definitions, they explicitly say this.
It's semantic games. Mass is the measurement of matter. It's not the matter.
It's what the definitions literally say.
Yeah.
They literally talk
what
about
you said. It said. You said it's a
You should be
measurement.
saying I'm not done more
It says right now is what it literally says.
All
So
right,
it literally
let's go
says
look.
that
Let's go check it out.
it's a quantity, it's a measurement, and it also refers to the actual mass itself.
Yeah, context matters when speaking English and any other language. Context.
I was arguing with the blowers about it. Some people were saying it's not a measurement at all. And that
So
was what I
I'm
was
reading
finding.
here. I'm reading from
Everywhere
Google.
I found,
Scott, I'm reading from
is
Google.
everywhere I found.
So
Okay,
tell me
hold
if
on for
you
a second.
disagree.
Let me finish my sentences though, okay? It's only reasonable. So what I was arguing with Globers about was not that that it had to be, it couldn't also be matter. I was arguing because they were saying it wasn't a measurement. And every definition I found said it was both. And so I was arguing you got to include measurement because it also is a measurement.
Okay, well, I'm reading right here, and it doesn't say both. It says mass is the measurement of the amount of matter. So it doesn't say that mass is the amount of matter. It just says mass is the measurement of the amount of matter. So I think you're wrong. You might want to go research.
Well, no, I think you're wrong because here's another definition.
We'll go read
it. And it says a coherent, typical large body of matter with no definite shape. That's a mass. A large number of people put together.
So the mass is describing the amount of matter. It's not the matter.
It can be both. Look, when you say that
no.
measurement,
okay, well, if this is what you believe, you're just wrong, and I'm not going to debate.
Okay, like the idea of you saying this is what you believe, you're just wrong, and I dismiss you.
It's what the definition says.
You
your definition says
you another definition that contradicted you. So now what do? You have to start looking into more detail.
This is part of the problem, Mr. Scott. We give you your
so if we look at a
scientific
definition of mass, so here's a chemistry dictionary, and if we look at the
just concede.
We get mass as a measure of the amount of matter in an object. It is also the matter in the object.
No,
literally, it says the two things.
Matter is bro. If anybody believes that, let me finish. Let me end on this. He's saying we know A equals A, right? A does not equal B. Matter equals matter. He's saying mass equals mass and matter because I need it to. Retarded.
No, it's literally what the definition says. Why don't you just look at these definitions? The measure of the amount of matter in the object. An object's mass is constant. It is the amount of it is the property of having mass. It is a body of coherent matter. It is a body of coherent matter. A body of coherent matter is clear. Look, if mass is defined as a body of coherent matter, then if I say a mass, I'm referring to a body of coherent matter.
Okay, let's Scott, put the dictionary down. Just put the dictionary down.
You're the one that brought the dictionary out, dude, not me.
Listen, okay. Don't interrupt. Talk to me like a person. When we say math,
if you want to get talked to as a person, you need to settle down with the no interrupts and the calling people retards and all your ad-homs and you're spazzing out. You need to just be talking like an adult. You do that. If you do that, you're going to get it back.
Okay. When we say matter, we're talking about the physical object, the matter. When we say a rock, we're talking about the rock, and we just describe rocks. Tennis racket. We describe the physical objects in general as having matter, right? Matter is not a specific term. Matter is a general term to describe physical objects in general. Can we agree on that statement?
Sure.
Makes up physical objects? Can we say that? Can we say matter makes up physical objects?
No, because a rock is not made of matter. A rock is made of whatever rock is composed. Hold on, let me finish. Because if you're going to say that physical objects are made of matter, then I'm going to say I have a tennis ball, a rock, and some water. And you're going to say, well, they're all made of matter. I'm going to say, no, the water's made of water, the rock is made of rock, and so on. So when you say they're all made of matter, you're wrong. So can we agree?
I think the issue is about the use of the word.
You agree. Don't tell me what the issue is. Say no.
I do not agree at all.
Stop trying to be so obnoxious. It's just ridiculous. Try to have a conversation where you try to understand where people are coming from rather than trying to dictate
Talk about what I said.
But this is the problem. I'm telling you stop interrupting. Stop interrupting and stop telling me what I can and can't say, and just listen to what I'm trying to say. And what I'm trying to say is this: that when you have a word,
don't talk about me though.
Are you done? Like, are you seriously this immature?
Don't talk about me.
Oh my God! All right, you know what? Right, just forget it. Like, you're just too immature.
See, now you're just talking about me. I just.
What do you want me to do? You literally interrupted me again. You literally interrupted me again to tell me not to talk about you when I'm in the middle of telling you what about mass. So it's like just nonsense. It's like you have no intention of actually trying to have a real conversation about this.
Ta-da!
Feel free to have them with other people. I will happily listen.
You figured that all out by yourself, Scott?
Okay, and that was my point. He just never defined matter or addressed my point. All he did was talk about me.
I posted a definition. I posted a definition in the debate chat box that suffices.
Okay, but I didn't ask for a definition, Scott. I asked for you to.
Well, no, it doesn't matter whether you asked for it or not. That's the definition that you need. You complained you didn't get a definition, so now I'm telling you did get a definition. Okay. And moreover, that definition makes the point that I'm trying to make.
Okay, but here's the thing. I was saying that a tree is not made of matter. It's made of wood. So if you're just going to go, yeah, but the definition says, I'm going to be like, okay, but
a tree is made of matter, though.
Hold on, but you're interrupting. Okay, so when I say that, when you say that a tree is made of matter and a rock is made of matter, I'm going, no, they're not. They're made of wood. A tree is made of wood. A rock is made of rock. Yeah. So don't you think it? Okay, don't you think it's?
Those are examples of matter.
No, those are matter is a vague description term, right?
It's general term, and those are specific types of matter.
Okay, so things aren't made of matter. Things are made of what they're made of. Okay,
they're made of matter.
Okay, hold on. So you're saying things are made of matter. So a rock and a tree are both made of the same thing, matter.
Yeah, and the general term for what these things are is matter. Now each of them has a specific thing that distinguishes them. But in the same way, it's the same idea that we had before. It's like you have trouble with this idea that words can be general and then they can become more and more specific with new words. So you zero in on a concept, even though all the words are under the rubric of the more general.
Are objects made out of a general term or specific materials?
Both. So they're made out of matter, which would be a general way to say it. And they're also made out of whatever particular molecule is in them, which would be a specific way to say it.
Okay, let me ask you again. Maybe you didn't hear me. The physical object itself, is it composed? Let's say we have wood. Now, is wood made of wood, or is the thing that composes wood matter? Now, what physical object makes wood?
Okay, so I'm going to tell you the answer to that. Wood is an example of matter. So a piece of wood is made up of matter. What kind of matter? Wood.
Okay, so I don't think you understand if I said car, right? If I said car, would a car be a specific object, or would it be a vague general term? Hold on, I'm not done. Would a car be a specific object, or would it be a vague term to describe things that Honda, Suzuki, Ford, that they make?
It's a general term for a type of vehicle.
Okay, so it's not a specific thing then, right?
That's right. But so Toyota is a car, and it's a Toyota.
Okay.
It was a car.
No, but here. So do you understand that if I said car, I'm talking vague in general. If I said 2012 Toyota Camry, you would know exactly what object I was talking about, right?
Sure.
Okay. So you understand the difference between saying a word like car and not talking about a unique specific object, and saying a word like matter and not talking about a unique specific object. Right?
If I said to you, do you have a car? Would you say yes or no? You say yes, I have a car, and then you wouldn't say no, I don't have a car. I have an Audi A4. Okay. That's not how you would answer. You say I have a car because it is.
Okay, but we're not talking about cars. We're talking very specifically about what.
We're not talking about cars.
We're talking very specifically about what trees and objects are made out of. Now, we want to be very specific because you're trying to quantify what is happening specifically. So you would use specific words. Like if I told you my car is fast, hold on, Scott, I'm not done. If I said that my car is fast, that wouldn't be specific. If I said I had a V8 turbocharged Toyota, blah, 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 that's where I start getting into the specifics. So when you say that, hold on. So matter is not a specific thing that compromises matter has no physical shape. Matter has no body. Matter is a description term. Now a rock has boundaries. A rock has shape. A rock has substance to it that is rock. Now a rock is not made of matter. Matter is a term to describe the rock in which the rock is comprised of. Now, if you disagree or go against this, this is an agree to disagree spot. So
you've monologued for quite a while now. So I'm going to take a short period of time, about a tenth of what you took, and I'm going to respond to our agree to disagree moment. And my response is this: the idea that words can start out be general. You can have words that are general that get a big idea, encompass a lot of different specific things, and then you can have specific words that zero in on it. Is not a hard one to get. In the same way that you say a rock is made of rock, it's a rock. Well, you could also say it's made of molecules, right? We know it's composed of molecules. Now, molecules are more specific than matter, but they are less specific than the particular molecules of whatever is a rock. I don't know what the molecules would be, but iron and whatever. And so we can have all these different words and all these different forms of language that allow us to talk about these things at various levels. And that's all that's happening here, is that mass is a way to refer to the material, the quantity of material that goes into an object, and you can refer, it's a measurement of it, and it is you can refer to the actual quantity with it. So when you say, I've measured the mass of that rock to be 15 kilograms or whatever, and then you can say, the mass of that rock is go grab that mass of rock right there, and we're going to put it over here, and you can refer to the actual thing with that same word, because that's the name of how you quantify it.
But it's not the thing. This is where you're losing. This is where you're just kind of like reverting to something that I can't understand. That you're trying to turn mass into a physical object. You're saying you can hold mass. And I'm going, you can't hold mass, you can't hold matter. You can hold a rock, and you can describe that rock that you're holding as having matter, but it doesn't actually have matter, because matter is just a description word you're using to describe, just like mass. It doesn't have
it's same
mass.
with rock though too.
This is the idea of like why the word salad in the baller community is how they build their entire model. Because if it was very easy and you would say matter, okay, so you have a rock. Do rocks attract rock? No, rocks don't attract rock. That's stupid. We should rocks do trees attract. And this is why they don't be specific about these things. Okay,
they do. All matter attracts matter, like in terms of correlation.
See, and there you go.
So trees and trees, rocks and rocks, rocks and trees.
I have so much stuff. I have so much matter on my table, and it's not all scrunched into the middle because matter doesn't. Yeah,
because it's not attracting it hard enough.
Because it's not.
It can't overcome the friction that it has to get through. There's a lot of other forces that are keeping that attraction force from doing the work. But it's there. It's trying.
It's just not happening.
Because the other forces are too dominant.
You make excuses for why it's not happening.
It's not excuses. It's an explanation for the truth. Yeah, it's because the other forces are too dominant. You can flap your wings and you're not going to fly. Why? Because you're not going to generate enough force. But a bird can flap its wings and it can fly. So it depends on the actual details. A law is a law.
Not all birds can fly, Mr. Scott. Penguins can't.
That's not true. That's a completely invalid way to look at that.
Then it's not a law.
Yes, it is a law because it's not saying that it happens in a vacuum, though.
Laws happen all the time.
It does happen all the time. It does happen because the law is not that it will actually move towards each other. It's because I get it because I can't get a word in edgewise. It's not the law is not that it will actually move towards each other. The law is that there will be an attraction force. The force may or may not be able to overcome the other forces. So the law does not say that. Hold on. Let me finish. The law does not say that they will definitely move towards each other. The law says there will be an attraction force between them. And now whether that attraction force is enough to cause movement, who knows? So your idea that this law is invalidated by the fact that things aren't moving is just it's asinine.
No, you'd be able to measure that force though, that tension.
Yeah, we can,
and we can see the objects are perfectly still.
We do with Cavendish.
Yeah, but Cavendish doesn't register a force. First, force is a conceptual word to describe a push or a pull. And this is why I say you have to be specific. So if you're talking about a force, so is gravity a pull or a push? We got to start there.
That's what I said first.
Okay, so it's a pull. So gravity is pulling the rock. How does it do that if it doesn't?
And not only that,
we don't know.
Hold on. If it's a pull, where are the pressure points on this?
How do magnets do it?
It's every molecule to every molecule.
The pressure is on every molecule. So if it's all equal, how is it pulling it then?
Perpendicular. It was all equal. I said every molecule and every molecule is pulling each other. So when you average it all out, you can also just treat it like the center of mass. But that's what's really happening is that all the molecules are pulling on all the molecules.
Yeah, but you can't have
magnets here.
You can't have a force without a pressure point, right, Mr. Scott?
Wait, say that, Kurt?
Magnets. Shout out for whoever mentioned magnets here.
Yeah, I was asking him.
What about magnets? We're not stuck to the Earth.
I was asking him how do magnets work?
Try to play with this.
Okay.
Magnets aren't gravity, so if you need to default to magnetism to prove gravity, you don't have
matter.
Non sequitur.
That's
well, maybe what you think is gravity is actually magnetism.
Red herring.
Maybe it's a form of magnetism.
If it didn't work with non-ferrous material, then that might be possible.
But here's the thing. Maybe magnetism does work with non-ferrous materials, and instead of and you just think gravity.
Yeah, maybe. I mean, maybe,
but
maybe we just. But also, it's like saying maybe we just call gravity magnetism and be done with it.
No, Mr. Scott, tell me why gravity is fictitious and magnetism is not. So is magnetism is a real force, but why gravity is not?
What is magnetism, Spurs?
No. I'm just wanting to know why we say magnetism is a real force compared to this fictitious force.
We can generate magnetism.
I think gravity is fictitious. Force is a perspective. When you use force, you think about force. It's a man-made concept that we came up with. Okay, it is a way to talk about the way in which matter interacts. It's a way to describe motion. Okay, and so we apply this paradigm when we want to use this paradigm. When we don't want to use the paradigm, we can apply a different paradigm. So when Einstein says it's not a force, he's saying, I have a new paradigm that's different. You can still use the Newtonian paradigm and it still works. All the equations work, follow. So it's really a matter of perspective.
All right.
Do you know why he said
hold on, sorry. In what way could we say magnetism is not a force in this way, in the same way? How can we use magnetism in the same way?
I don't know if we can.
Because it's a field.
Yes, but you're saying that with gravity we can say it's not a force and it is a force, but with magnetism it will always be a force and never be a fictitious force, right?
Yeah, there's an alternate sort of framework that we have for gravity that Einstein came up with.
Sorry, right now, go ahead. I'll just ask that.
No, go. I'm just listening because you're basically saying the same thing. Well, one, Spurs raised a great point. Where are the contact points? If I drop a rock and you said it's a pull, is it being pulled from the top of the rock as well as the bottom? Because if you're saying every contact point,
everywhere is a contact point. Everywhere.
How does it pull from the top?
It pulls on everywhere. All molecules.
No, I didn't ask. I said how. Like I can understand.
We don't know how.
Well, then what do you know?
The how of gravity, the how it works is a mystery still. We don't really understand.
It's a pull? How do you know it's a pull force then? If you
it behaves as a pull. It behaves.
How do you know maybe it behaves like a push from above?
Because it goes to the center of mass.
Right. It could be a push, and we'd be surprised, right? But when I say it's a pull, well, what I'm saying is that it appears to and behaves as if it was a pull. Now, it may turn out that angels are pushing it. That's possible. I won't deny that. So it could. I didn't want to. Hold on. I didn't ask what you asked, right? Let me finish what I'm saying, dude. So it could turn out that it's a push from some surprising way. It may be angels. It may be not magic. It may be something very scientific. It could turn out to be a push, but when you look at it, when you're thinking about it, when you're observing it, it appears to behave as a pull.
No,
and of course that's not proof that it's a pull, but it appears that way.
The hallmarks of a push, we can see there is a press, there is pressure. So we know that's a signature for a pushing force. Now you're saying there's a pull. As right hand is asking you, how can we recognize this pull? What indicators?
I think if you look.
Mm-hmm. Yeah, how do you?
I think if you look at the way that planets distort with gravity, I think that's indicative of a pull too. By the way, like if you look at a tidal locking, I think is uniquely associated with.
No.
I'm asking, how do I tell the difference between a push from above or a pull from below?
Like I said, by looking at the distortions on the objects themselves.
Okay, so what distortion?
You're moving away from the point. Away from the point.
No, hold on. This is important. So you said you can see the distortion on an object, and that'll tell you.
I think you can see it on planets. Yeah.
You think, or you know?
I think. Okay,
so we're getting into.
I'm not a professional physicist, but I seem to remember that if you look at planets orbiting it or headed towards tidal locking, there's a distending that happens where the part that's going to be tidally locked gets pulled, it gets stretched out a little bit. I could be wrong. I won't quote me on that because I'm not looking at anything. I'm just remembering this from years ago. But I seem to remember something like that.
Blackwater says tidal locking is debunked because if mass of the sun can affect the Earth, if it can affect the moon.
But it doesn't debunk tidal locking.
Yes, that debunks.
I mean, he's right. The gravity affects both of them, but it doesn't debunk tidal locking. You guys got to remember that different forces have different strengths, and that they all have to be combined together.
Forces are concepts. So please, when you say we're trying to let me explain something. Now, one of the problems with
observations.
Okay, let me explain this. One of the problems with ball Earth. One of the problems flat earthers have with ball earthers is that you just use these vague terms. Like you'll be like, well, there's a whole bunch of forces acting on this thing. And then when somebody like me comes in and goes, well, force is to describe a push or a pull. Now, is it being pushed or pulled? And you go, well, we don't know. And I'm going,
well, no, we said pull, actually.
Well, yeah, but with others, like, you know, okay, but then I try and say, okay, well, how is it being pulled? And you're like, wow, we don't really know.
Well, we don't know the answer. There are mysteries in the science. I'm afraid you're going to find the
How on earth is that acceptable, Mr. Scott? What? Show us a pulling force.
I guess
in
it
nature.
isn't. You know, it isn't. It's that's why science is constantly progressing. It's why it's one of the hottest. Hold on, Soros. It's why it's one of the hottest areas for research right now. People are desperately trying to figure out just how to solve the mysteries of gravity, and it's a big deal. And it's going to be a big deal when they solve it. But the fact that it's a mystery should be exciting and thrilling to you. It shouldn't be a sign that somehow science is failing. It's a sign that science is doing exactly what it always says it does.
Exactly, and we know enough about gravity to understand how it's going to react when we do things with it. Now, the idea of a push and pull, that you got to understand the concept of all the molecules, all the mass, all the matter, whatever you want to name it. Whatever you want to, what level you want to say it at, is being affected by the effects of gravity to the center of the Earth. That's why when you throw a ball, it always has that arc, because the moment you throw it, the energy you put in it is leaving that object, because Newton's first law is coming into effect.
But Mr. Scott, you're saying you won't concede because you're waiting for a future experiment. There is an actual pulling force, because right now we know
not even remotely what
because
I'm saying.
right now
I don't even know what you mean by conceit. What are you even referring to?
Exactly, you've got nothing to replace it with, chemo.
That's what I'm saying. You're prepared to wait and sit there in ignorance. You're being. This is what you would say. This is ignorant. Right, you're waiting for a future experiment.
You're making no sense to me. You said I'm not letting you concede, but what do you mean concede what? Because I don't know what you're talking about. What do you mean by concede? Concede what?
That gravity's not a force.
No, that has nothing to do with this. Yes, I'm not. Yes, you're right. But I'm not waiting for future experiments. That's by definition. I've told you this already.
We know there's no.
That's already established.
We know there's no.
Of course there is.
You can't demonstrate.
And there's no need for future experiments. I don't know where you got this idea that we're waiting for future experiments.
Right.
This is all in the past.
You just said we're waiting to find out if we can demonstrate a pulling force.
No, we're waiting to find out how it works. Like what's actually going on. Why does gravity break down on the quantum level? Why does it not work at very large scales? What's really happening underneath the hood? We don't really understand what's causing it.
We're talking about pull. Where do we see pull?
Okay,
everywhere we see gravity.
Go on then, let's see it then. Show us how it works.
Conceding that you don't have a replacement.
What's the mechanism behind this pull?
We don't. That's the part we don't know. Is how does it really
you
work?
You are banking all this on a future experiment.
I have a rope. It's going through a hole in the wall. I'm pulling against that rope, and it seems to be pulling back against me. I don't know what's pulling that rope. Is that rope not pulling? I have no idea what's pulling it.
What if I told you that there is no pulling force?
Yeah, go ahead.
What if I told you there was no pulling force and the push? Now you're going to say, well, what if you pull? Here, let me prove it. Now you're going to say you pull a lever. No, you push the lever from the other side.
Oh yeah, you push the lever. I agree with that. You definitely push the lever.
So show me a pull. So show me an actual pull.
What about a magnet? What about magnet?
No. See how they always revert to magnetism?
Well, you said show me a pull. You talk about a lever. You're not going to get any argument for us on levers. Levers are clearly pushes. Okay. So here's an example of a pull.
Well, what's the mechanism behind the magnet?
The lever's obvious. We all agree on that one. But
what's the mechanism?
So you don't know.
How is it pulling? How is the magnet pulling?
Well, how is it not pulling? You put the magnets together and they fly together.
Well,
okay.
Tell us the mechanism.
What's the mechanism?
How do magnets pull?
We know the mechanism for magnets.
What is it?
Magnets.
Really?
Say it.
It's all the electrons being aligned in the same direction, doing electromagnetic attraction.
Why does that cause a pull?
That's electricity then, not magnetism.
Because we don't know why I guess I don't know why they're actually attracted to each other.
Same as gravity.
So you're dealing with electricity.
Yeah. Well, obviously everything always breaks down to a no. We don't know the answer eventually.
That's right, Chemo.
We're at the exact same place with gravity, though. The exact same.
I think we know more about. No, we know more about magnetism.
We can go deeper with not knowing than they can.
All it is electricity. No big deal.
Yeah,
Scott, do we know more about gravity?
I think so. I don't actually know much about electromagnetism, to be honest with you, but that's my sense of it. Like when Coulomb's Coulomb's law and all that Coulomb stuff, isn't that a very robust explanation? And Maxwell's equations, aren't they a very robust explanation of electromagnetic attraction?
No, electricity.
Not explaining the why.
Electricity is a push, so magnetism is just electricity. So it has to be a push from the outside, which is causing.
Yeah, that's not true though.
Yeah,
it's just not true.
That's what's happening here.
I mean, look, you can say, look, don't get me wrong. If you want to reimagine everything as pushes, you can probably get it to work out. Now, I bet you there's some experimental tests that would cause problems. Like if we, again, we could look at objects that distend, and we could see, well, if it's a push, it should be distending in a certain way versus if it's a pull. But you can reimagine everything as a push, I guess, and you probably get it all to still work in a theoretical way, and that's okay. Science isn't really designed to, prove to with absolute certainty that it can't be some alternative that's, clever. The question is it a likely alternative? And then that's, I think, where it shines.
Let me ask you this.
Science tries to find the most likely alternative.
Okay, if you were talking about likelihood, can you explain how an electron bouncing or coming off can create a pull force? Because then we're going to get into the unlikelihood of your bouncing particle idea of the world and how it can never manifest as a pull force because it's only an electron coming off. Well, so can you explain a pull force in your model with your bouncing atom?
So I think it can be. I'm not the guy to ask because as I said about 5 minutes ago, you must not have been hearing. All I know is that I think, and correct me if somebody who knows better, Maxwell's equation, the Coulomb's law, does a very good job of describing how this pull effect occurs, this electromagnetic effect, this intermolecular effect. Is that someone here actually who knows more electromagnetism than me probably should jump in and explain?
No, but you're the math PhD.
Okay, so you don't know.
Yeah, but I'm not a physics PhD.
No, but you're the astronaut.
Okay, but so you also
you're
believing in something you don't really. You're believing in something you don't really understand.
So electromagnetism is not a real
on
thing
some
now.
level, though, I don't understand anything on some level. Like if you go deep enough, my understanding of everything is going to find a limit. And that's okay. That doesn't mean that I just am arbitrarily believing in things. It means that I don't have perfect knowledge of anything. And I have a series of confidences and likelihoods and evidences, and I combine all those things together to create a world model. And that's what you do too, whether you admit it or not. And if we go deep enough, you're going to say I don't know too at every single thing you say that you know, or you're being perverse. And it's not a bad thing. It's nothing. There's no shame in that. That's okay. That's the way the world works.
But I have God, so I can always say.
Okay, then you can say that's absolute. Sure. Yeah. Okay, that's cool. You can say that.
Yeah, but that still means you don't know.
That's a nice.
No, I know. I know God made the system. I know.
Yeah, but you don't know how God works, or who made God, or
nobody. It doesn't explain anything.
Yeah, but Mr. Scott, how do we get you to recognize that you're then being dogmatic?
Did he create it with a push or a pull?
You're being dogmatic.
Yeah, you just have a one-track mind. You're saying, well, until we have a future experiment to prove what I'm talking about,
I didn't say a future experiment. What are you talking about?
Because we don't have a pulling force. We can't demonstrate this
we
pull.
do.
Right? And you're saying the
I'm not asking for a future experiment to demonstrate that. I've never mentioned anything about this. And again, I'm not one track. I just told you it could be remodeled as a pushing. Everything could be remodeled as pushing. I'm not saying you couldn't do that and be clever about it.
It's not going with the could be.
In what way? Is the point, if I'm saying that you could do that, and that might be another model which describes this stuff.
So go with the right now. Go with now. What can we do right now? We can't demonstrate pull right now. So
we can.
So what you should do is concede until. Why not reserve judgment and concede?
Why not look at Cavendish and all the subsequent Cavendish experiments? They're doing a good job of establishing pull.
Use a drinking straw and drink a drink out of a glass. You're pulling the drink up the glass, aren't you? Up the straw.
That's technically push. That's still push.
You guys will say that the atmosphere is pushing.
Yeah, that's the atmosphere is pushing the water down.
Is pushing down. So know your own model, dude. Come on.
Here's
another.
Don't need to be obnoxious. Everyone has different areas that they know better than others, and none of us are experts. None of us are professional physicists. I mean, there's no need to be obnoxious about somebody not getting every single thing they say perfectly.
An expert in anything.
Here, this is the big
pushing
problem.
down the atmosphere. That's another lie. We say. You say. We say.
Yeah, I know. This is the big problem.
Just lied again to make a point that's not true, and you said, "I know."
Oh boy, no! You guys say the atmosphere pushes down the soda. That's why it goes up the straw. Don't
that's true. That's true. I say that.
Hold on. The atmosphere is pulled down, and the layers of the atmosphere push on each other. The lower layer beneath it is pushed on by the layer above it.
Talking about a straw, sheeple.
Yeah.
I'm talking about why the liquid goes up with the straw in your model.
It's
in your
kinetic
model,
push there.
It's technically a push in your model. So don't come on, man. I don't back stuff I didn't.
Why are you poisoning the well here? That's what Mr. Scott
He's not.
said.
It's just a confusion. That's the point of confusion over what we're all talking about and what specific thing. You guys need to be more generous in conversation. Like, there's no need to try to get everything to be a gotcha. It's just silly. It makes it so.
I'm not trying to. I'm just look. I was just like, look.
I was talking this first.
So here's the thing. When you're saying we have this knowledge, like you're like, we have this deep understanding of the world. And I'm like, wow, bro, I want to understand the world too. So I'm going, okay, I see this rock fall. And you're like, yeah, we know all this about it. I'm like, okay, great. Now, how does it fall? And you're like, well, we don't really know. I'm like, oh, well, what is it, a push or a pull?
Here's the problem.
Like, hold on, I wasn't done. You just interrupted. And I was like, well, is it a push or a pull? And you're like, it's a pull, but it can also be a push. I'm like, well, if you can't explain the mechanism, you can't explain why any of this is happening, what do you really know, though?
Okay, so here's the problem. The part of the beginning where you said, well, you guys will say all this stuff. Now, I do not doubt that you run into people that talk like that, okay? No reasonable person who has any understanding of science at all would ever try and talk like that, because that is not what science purports to have. That science does not have this absolute deep knowledge that cannot be questioned. It does not have the answers on high delivered to you. It is quite the opposite of that. It has nothing it says can it prove to be true. Everything it says is something that it can present only with probabilistic likelihood. It is the opposite of saying it has knowledge that it can deliver to you, and you're going to be, you're going to have the final answer. Now, you've heard people say that, but you haven't heard scientists say that. You've heard people who are trying to pretend to be scientists. You heard obnoxious trolls. If you talk to people like me or other people in this Discord, in this particular Discord, you're going to find lots and lots of people that give you an opposite rhetoric. But yet you keep coming at us as if we said to you, we have the answers on high, and here they are, the final answer.
You're telling me you're like, we know gravity. We know more than the rock falling. I'm like, okay, hold on, let me get it out. I'm like, okay, so you know more than the rock falling. So you understand the why and the how. So give me that. And then you can't. You can just say, well, we know that maybe it's a pull from the bottom. Maybe it's a push from the top.
What we can tell you is how much protraction there'll be based on how much mass and how much distance. And that's something that was figured out by observation alone. Okay, we observed
which
how
I
the
can
world
figure
work.
out, right?
Well, it's hard to do, but if you were presumably in theory. Well, no, I don't know if you can do it. I mean, the model of gravity is what it's describing. But there's other, you can call it something else. But when Newton comes up with that equation, right, that's the thing that we have, and that's different than just saying things fall. That's saying how fast they fall, how fast they accelerate, and what the factors that determine that acceleration are. That's information. That's more than just it falls.
But all that information I can get from reality through observation. I don't need a theory of mass attraction.
Well, that's how they did it. They did it through observation.
Yeah,
they did it through observation.
Why do we need space-time bending as a theory? Why do we need mass attracting mass as a theory?
That's because I'll tell you why. That's because the observations at some point when we got good at making really, really extreme observations, we found observations that contradicted Newton's equation. We found the transit of Mercury didn't work.
But you didn't,
for the first time for Horn.
That wasn't my question. My question was, if we're only going with what we see, right? We're going with what we see and what we know. Why do we need what we don't know? Because then we'll never be wrong, right? So if we have our observations, nothing can break down. We'll just make a new observation and a new effect and just put it into our model. When
we don't have what we don't know.
Hold on.
We don't have it. We just have words for the thing.
If we only observe reality, right? All we did was observe and quantify reality. Could we ever be wrong?
Well, yes, we can, but that is what we've done with gravity equation.
How could you be wrong by measuring reality? Where would you be
Because
wrong?
you may not have measured it completely. So you may have measured reality, you may have gotten good measurements there, but you have cases that you haven't encountered yet. So
give me an example.
You'll discover that. Well, Mercury's transit, the one I was just giving before. We have 400 years. We had this equation that we thought was perfect. Well, it doesn't matter, but we had this equation we thought was perfect, and then we had an observation that broke the equation. The equation no longer applied. It was no longer universal.
Not done.
Here's my point.
And so when
the point is you had the observation before, right? You had an observation of the sky. Then a couple years later, they're like, oh, we didn't observe this thing. And we're like, oh, okay, we'll put it in now. Like, okay, we put it in. See, when I do that, nothing was wrong. Nothing had to get replaced. Only something was added to what I already had. I didn't need to change anything.
Okay.
Now hold on. You have to change. Let me finish. This is the point. You have to change things. You have to change your model because you're making guesses. You're making things that are based. Yes, that's why you have to change them.
No,
because
I don't know. When you said you observe reality, what do you think you're going to come up with that's different than what Newton came up with? If you're going to be able to do the same thing he can do, which is predict the amount of acceleration that's going to happen based on size, mass, and distance, what are you going to say that's different than what he said?
Okay, because what Newton is going to say, he's going to say some words. He's going to be like, I think a body in motion, but blah, 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 blah. And I'm going to be like, I'm going to be over in the corner dropping rocks of different sizes while he's thinking in his head about stuff. And while he's thinking in his head about these laws and just coming up with words, I'm going to be dropping objects and quantifying how fast they fall, bigger and smaller. And I'm going to start building a catalog of how all of these things interact while he's over there thinking. Okay, now
that's the exact opposite of how it happened, though. He did was build a giant catalog of how it actually fell, and then looked at this giant catalog of how all these things moved and fell, including 10,000 observations from Kepler, and then started figuring out, okay, it was a huge catalog. It was like a lifetime worth of work. And is there a way to make all this cohere together into a universal understanding? And what he ended up with was a simple equation. He's not saying anything beyond the equation, which is the observation of reality, which is the exact same thing that you would come up with if you looked at the observation. If you were going to have something that was equally useful, you'd say the same thing he said. So I don't see what your complaint is. I don't. What could you say that was different?
Here, let me tell you. I'm not using the thoughts in your head. He's going, I think a body in motion. Well, that's thoughts in your head, right? So that thought in his head. Hold on. Don't. When he's saying, I think a body in motion will stay in motion unless it's acted upon by forces, a concept, these are all thoughts in his head. Now, when you take a rock or an object and you lift it up and you drop it, that's the information. His laws of motion don't give you information. They give you nothing to work with. When you go outside and you drop a rock and you drop that's where you get your information. That's where the model
But we're talking about law of universal gravitation.
No.
And what I'm saying is, what would you come up with differently than he came up with? You're saying that there's no need to, why not just do the observation of reality? And I'm saying that's exactly what he did. And he gave us this equation. And I'm wondering, what are you going to give us? If you did it your way, what do you think you would possibly have that's different than what he did?
Okay, because an equation is nothing but little numbers on a piece of paper. And the problem is your equation.
It's a description of reality.
No, it's not a description of reality because they break down when you apply them to quantum or to other things. So all you did.
It's a description of a certain amount of reality.
Okay, but the problem is, what's the only thing that doesn't change is the observation of reality. So we know the rock will fall at X speed. Now you come up with this equation, right? And you're like, we nailed it. We got this rock quantified. We know reality. And then at the quantum level, it breaks down. You're like, shit, we have to go back and get a new theory. Yeah. So basically what you're doing is you're trying to connect all of these interactions somehow. So you have the lights in the sky moving over your head and you drop a rock and you're going, we need to connect these somehow. And you just basically all you're doing is doing a brute force password to an equation. Yeah. If you took 1,000 computers and just started having them plow away, they would eventually get you a math equation that works with everything.
In fact, they did this.
And
they had a computer look at the same data that Newton had. I'm too excited to tell you. They had a computer do exactly what Newton did, and it came up with the same equation. You're absolutely right.
But the equations are still wrong. The equations are still wrong at the quantum level. That's why they're still searching for which they already have.
But here's the thing that's important is that for the observations that he had available to him, this equation works perfectly. And it does work perfectly for a huge number of observations. It certainly works perfectly for everything. Hold on. It works perfectly for everything at our size levels, right? Now, it doesn't work perfectly universally, and that's why we have to keep modifying it. That's why it's one of the biggest mysteries still. But the thing that you seem to keep missing is that there's nothing to it other than him saying, here's a correlation between mass and distance that tells us the strength of a force. That's all he gave us, okay?
No, he didn't do that.
Yes,
he
did.
He gave us an equation. He gave us an equation.
The equation it tells us the strength of force based on mass and distance, and that's it.
No.
Now, if you don't give us that in your version, then you aren't giving us anything useful. He's giving us something useful that we can actually use that works.
Let me tell you why he's not giving you anything. So an equation describes reality. So when you say, so all you've done, right, is in another language describe how fast the rock falls. That's all you've done. And instead of me saying a rock falls at 9.82 meters per second, you're just using math. You're just using another language to describe what we see.
The mass and the distance.
Okay,
so we've been able to
measurement of matter. Mass is a measurement of matter.
But we're able to tell you the force in terms of other things. So what's useful about that is we often might have a situation where we know the mass and we know the distance, and now we want to know how are these things going to interact with each other? And this equation gives us this information that's going to be new in this case, right? Because we don't have that.
Okay, you're not listening. So I'm going to say this one last time, and then if you just want to address something else that I said, then fine. I guess we'll agree to disagree. So listen to what I'm saying. An equation, okay, only describes reality. So you can't use an equation for something you haven't observed in reality. It doesn't work like that. Now, if you're going to say, well, yes, we can, that only means you have a set way reality works, you've quantified it into a language, and then you're going to use that language to make what you call a prediction, but all it is applying the knowledge, right? And this is where the entire disconnect is. You think you can prove your theories when they match hold on, I'm not done. You think your theories have some sort of empirical weight to them when they match the observation, even though your theories need to be changed when you make new observations that don't match, because you're trying to fit everything. Hold on, you're trying to fit everything into a universal math equation, and you're saying gravity is this mass equation of force and acceleration, and see how everything works with it, therefore the equation must be true. And I'm saying, no, that's not how reality works. And if you do, then we're not on the same level. You're giving math some kind of magical abilities that it doesn't have.
So much of what you're saying that we're doing is so far off the mark. It's weird. Now, on some level, some of the conclusions you're saying are what we're saying. And you just don't understand that. You're not hearing us is what's really happening, I think, because you keep applying this image you have of what mainstream science is. And you keep sort of painting us with this attitude of, you think this proves this. And we never don't think any of that stuff, okay? And moreover, you're right. It is a description of reality. Now, I think that you're quibbling over whether a prediction is or isn't something that can be done with equation. I think that's quibbling. I think that you're abusing the word prediction. It's sort of beside the point. But the truth is, when we come up with this equation, what we find is that when we then create novel situations, novel values for the variables, i.e., we look at something that says something that we haven't seen before, the equation predicts what we're going to see in terms of the force. And so far, for 400 years, we had been not finding any misses. Every time we had a new situation, this equation held up. And after that happens enough times, you start to get some confidence in it. You never think it's true proof-wise. You always know eventually you're going to have to revise it. The entire history of science is a series of mistakes, corrections, and revisions and improvements. All it does is fix itself. So it's never done. It's never right about anything. Every single thing that we know in science today is going to be wrong or improved or different in some way in 1,000 years. We're going to have made a change to everything. And that's good. That's how science progresses. So
why do you tell us mass attracts mass and space-time bends?
We don't.
Just say the rock
that this is what we say. And I've said this so many times and you never listen. Here's what we say. It looks as if, or it behaves as if mass is attracting mass. They are correlated. But what's really happening underneath the hood, it's unclear. It's hard to know. But it certainly can be talked about or modeled like mass attracts mass. That's an easy way to talk about it, but that may not be what's actually happening. So I say it's correlated. Mass and distance are correlated with the attraction force.
Okay, so what you're saying is this is my point, and I feel like you just made it, but we still don't disagree for some reason. So you're saying what we know, the most certain thing we are about is that the rock falls. Now we have things we're not certain about, which is maybe there's this pulling force of attraction, maybe there's a pushing force of repulsion, like these kind of things we don't know. But what we do know is what we can see and what we can quantify. Like that's what we know.
Right. I wouldn't say that when I was saying the thing about the push force, I'm saying you have to leave open the possibility that these things are true, right? It's possible. I don't think that's likely at all. I think I'm very confident that it is pulling. It certainly behaves like it's pulling. I don't know what the mechanism is, so I could be wrong about that, but everything about it, you might as well just call it pulling because there's nothing about it that seems like it's a push. And I have to look it up, but I bet you I can find some experiments where the distortions are such that are consistent with pulling and not with pushing. So I think
let me ask you this. This is very important. If you telling me that it's a pull, but in every ounce of imagination, you can't give me a mechanism, and you're like, I just can't explain how it's happening. I'm going to be like, well, I cannot get on board with you that it's a pull force or what. I can't get on board with anything you're telling me because you can't really tell me why it's happening. You can only show me what is happening. And I can see what is happening. I want to get with somebody that knows why it's happening.